CBAM, and it's what we do how we do the pre. The first thing is why we need to do the fabric detection based on the AI technique. It's because the traditional methods were always based on the professional skills and the experiments of human. And sometimes the human will feel boring about what they are doing now, and they will feel tired, and it will make some error. And for some companies, they will return back all of the product if they find any defect in one sample. So it will cause a big loss. And if we can use AI technique to help, it can really reduce the detection speed and improve the detection accuracy. And actually, there's some drawbacks in AI technique because we don't have enough exacting fabric detection database online. Most of the database online is built before 2010. Most of the image in the database is low quality image, and they always gray level image. We cannot say if we can detect the gray level image, we also can detect the quality image. And I just choose some paper published in these 2 years. And interestingly, is most of the paper are written in Chinese. I guess because textile is an important industrial in China, so we have more data to collect from the industrial. And actually, most of the recognition based on the Faster RCNN. And before 2020, I remember 2015, most of the paper will focus on use other way to detect the fabric detection, but they find we don't have enough data. So they have two choices to do some research in this area. One is use the Faster RCNN to do that detection, and the other one is use like GAN to train the model to build some defects image. And I just explain some drawbacks about the English journal. The first one is exploring first RCNN for fabric detection. This paper is published at 2020, but the database used is built in 2007. They have about 150 defects images and 1,000 defect-free image, which means it's very hard to train a database to train on Faster RCNN. And they believe their model can do a real-time detection, but actually the image in the database is quite small size, and I don't believe it can detect a large image or do some video detect in the real time. The second one is published also at 2020. They said they have a really huge amounts of database of data, but actually they didn't realize their database. So I don't know if their database is the quality of the database. And it's called PRAN net. It means a priori occurrent neural network. It's a modified one part of the Faster RCNN, the region proposal network. So it's also based on Faster RCNN. And we also try to based on Faster RCNN to do it because up to date we don't have any researchers to try to use other database, try to use other model to do it, because I don't know why, because it's a little strange, but it's first time we also use it. The Faster RCNN, most of the researchers will try to modify the backbone nets. This part is we use ResNet 15, and as I mentioned, the last paper is modify the RPM parts. They just change how to propose the occurs, and we also try to define because in the we can improve about the feature map, we can get high accuracy. And the method we used is this convolutional block attention model. Why we choose it? Because that's because the second attention model, this spectral attention model, is very unique. And it's the structure of the attention model. The first one is the channel attention model. And actually, it's just use a variable pole and max pole together to improve the performance. And if the squeeze and excitation network we call IC-net is has presents that if we use a global variable pole, we can improve the performance. So it's not very charming, but this part is is very useful because they think if we add a max pole and a variable pole and use it and turn it into a convolutional layer, it can improve the performance because it's called this party can train the network where we want. And unfortunately, the author just said we add this layer based on the experiments, so we don't know why it can improve the performance. So for us, we just believe yes, we can use it. We also can now understand why it can improve the performance. And in the experiment part, the fabric we used is an patent fabric, and it's a little different from the existing database online because we do not use the industrial fabric, which means the fabric is quite simple and it have high repetition rate. You can easy to classify which part is the background and which part is abnormal. And what we do is it's from a webbing company. Yeah, it's a cooperation project. We cooperate with a company, and you can see this image is not so repetition, and we in this project we only have 3 different defects: it's drop needles, broke holes, and fly yarn. To augment the data set, we also do some flapping and distort method. The database is contain 158 defects image in 3 categories, and the image source is from a switcher company in China. And we cannot release this database now. We need to. I hope we can release it in the August after they accept it. And it's a cooperation project, so we also need to focus on how to apply it, how to use it into the real life. So it's an important thing, but I guess most of the network doesn't think it's quite important. It's the fixed condition threshold, because most of the RPM parts just use the fixed confidence threshold, which means if the confidence of the objective is above 0.1, we will think it's a true point. It means if it's above 0.1, it's a defect. But actually, it's a textile, so we cannot get the perfect image. Sometimes we have some cracking, sometimes we have some shadows on it, and like in this image, this one is the true defect, but these 2 parts just some press, and they also think the network also think it's a defect. So we have to modify it. We have to change it into a better way. And for us, we think it's quite like image processing, because it's a threshold, and if the confidence larger than the threshold, we think it's 1 is true, and if the confidence is less than the threshold, we think it's 0. It's defect free. It's just like how we transform a gray level image into a binary image. I mean, if you get that one part, is the light part, and it's less than the threshold is the dark part. And because we are worried about the time consuming and the computation consuming, so we just use the simple way to detect to modify the thresholds, and it's the second order that difference method. And I guess if we use some much complete method, it can improve the performance, but we don't know if it will add the time consuming. The result shows the left part is what we can get from the RCNN, and the red part is what I can get from the CBAM, the RCNN with CBAM. Definitely, you can see the confidence have improved, and even for some overlapping image, it also can get improvements. And in this overlapping accuracy, we just use in this project, we just use an AMS to do it. I guess if we use soft AMS, we can get better performance, but not in this project because it's a cooperation project. So sometimes maybe I cannot say too much about those things. And this part is cooperation of the RCNN and the RCNN with CBAM. You can see it can improve the performance, and the accuracy is just improve about 0.01. It's because the drop needle image takes a large part of the database, and actually it can improve the performance of. And this part is if we use self-adaptation confidence threshold, and if we didn't use it, it can improve the performance. And in the conclusion part, in this project, we have proposed effective fabric defect detection method based on the Faster RCNN with CBAM. It can detect 3 different fabric detection on the unpatterned fabric. And actually, it's very hard to detect the fabric on the patterned fabric. I mean, maybe it's not the methods. Maybe not the methods cannot use on the pattern fabric because we don't have enough data, and we cannot tell the model that this is a pattern, is also a normal part. We cannot do it, so it's also very hard. And I don't know if we can fix. I don't know if it can be fixed in the future because we still don't have enough data. The second one is we compare it with the Faster RCNN, and we think this method has significantly improved the performance. And the results show that method can be applied in the manufacturing. And yes, it can be applied in the manufacturing. And the disadvantages is also lots of, because first one is we don't have the comparison with other exacting algorithm because we use different samples, and the training sample and the test sample is quite different. So I don't think it's worth to do the comparison, and I cannot say it's really good or other algorithm is bad. The second one is this method cannot be applied in inspecting in the real time because it only can detect 1.8 images per second. And also it's very hard to detect some small defects because if what we input the image is not so small, and if the defect is small, it's just ignore it and think it's a normal part. Actually, I cannot say how. I just think if we want to solve this problem, maybe we have a test like before we input the image, we just segment the image into a small part and then input it. I'm not sure. And the last one is we just can detect 3 different defects, and it's really small because there are about 85 different defects in the manufacturing. three different defects is not so useful. And in field work, the important thing is we need to collecting more defects data to update the database. And the second one is also important is we need to reduce the model's requirements for the image quality and the illumination continuation, because we think in the fabric manufacturing processing, we cannot always support a very perfect image. And the second one is we need to improve the self-adapting confidence threshold method, because I think we just use a simple one is not the best one. And the last one is we need to detect more classes of fabric defects, and we need to detect more different structure of the type of defects. And okay, that's all. Thank you.
Okay, thank you very much for an interesting presentation, and you're getting some applause also. So any questions first from our audience here, and then